You start believing the universe is working in your favor. Remember, the universe.
Yeah. How are you?
I'm good, Sensei.
Zamira san,
Yes, Sensei.
uh, Tara-san, will you join this meeting?
Uh, I will. I will ask her later. It should. He should be. She should be joined today. I
I
will
know
call her later.
you do it.
Mm.
Well,
Sarah.
so, okay, I will send her email. everything okay?
Yes, sir, I'm good. Everything is going good.
Uh-huh. And okay, so you will come to Japan this month, right? Next week.
Yes, sir. Next week, sir. Yes.
Oh, okay. Okay. OK, so shall we start?
はい。
えっと、ダフィラさん、I
Hello.
asked you
Yes,
to
sensei.
find the viscoelastic damper, and
Yes.
you sent me
A few paper. Yes.
paper.
Mm.
Can you, how to say,
Yes, sensei.
could you show me mathematical formula
Uh,
of the damper?
okay, I will share my screens. Okay. Sensei, I think Sarah-san is on the way joining the meeting. She replied my message. Okay, can you see my screen, Sensei?
Okay, yeah.
So, in from the paper that I gave, excuse me, I found a few paper that have equation that related to how to calculate the effective damping of the elastic. So this one from Christopoulos. I still study about this paper. So, and then so basically based on your summarize from the paper of Nike-san, I realized that we have the effective damping here. This one. So here in this graph we have C1 and C2.
Yeah.
And if you can see in this paper also have similar graph. Here K1 and K2, but for this paper it's using matrices. So the concept is from this is the model, so basically same as our model, and this is the in the middle beam they have considered this as a spring. So and it starts with this matrix. So basically we have uh, the beam here, we have the moment, shear, and the axial force and displacement for the both and beam, and in the middle we have this stiffness of elastic damper, viscoelastic damper, and they put the equation in this matrix to calculate. And this is the axial loading, energy displacement, effective bending moment, and the shear at the end of the element without any impact of axial loading. But this one is a bending moment and shear. So basically here it consider the displacement only equal to 1, and other how can I say, other fixed only one variable, the data are equal to 1. And the second one use the assume that the rotation is equal to 1.
Yeah,
And
yeah, yeah. They try to get the stiffness matrix better.
mm,
Where is the property of damper?
properties of damper, here
Why damper formula is? Could you
go down
tell me? Yeah, it looks bilinear hysteresis.
by linear hysteresis.
Is it viscoelastic damper?
This is viscoelastic.
Is
let
it
me
mentioned?
let me show you. Damping, it is only damping, and
Looks
this
like hysteresis damper.
so only this one is viscoelastic temper.
Yeah, 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 yeah,
Yeah.
yeah. And stress strain relationship is
This one, Stephen.
GE and GC.
This one and this one.
I mean, equation 5.
Mm.
Yeah, well, 3 and 4, well, equation 5.
Mm-hmm.
So, if GC is constant, it is
Mm-hmm.
something similar to oil damper.
Okay.
But if it is viscoelastic,
Mm-hmm.
uh, the formula is not this one.
Okay.
And let's see. So if viscoelastic,
Mm-hmm.
uh, this will be, let's see, and velocity part multiply some power of alpha and also some coefficient c.
Mm-hmm.
But this is I'm just a velocity, so it looks like uh, oil damper, or I don't know. They call it it's a viscoelastic material.
Mm-hmm.
Is GC is constant value? Where the
GC.
GC? I mean,
The properties.
value of GC.
Let me check. I saw here in table. GC. Viscoelastic temper. Doesn't give it here.
There is no GC.
This doesn't mention here. It's only give for the optimization and the design example.
So,
GC. This is also not.
could you go down?
Go
I want
down.
to see the picture. Yeah, stop.
Okay.
Okay. Is there any table
Uh,
about the parameter in this
parameter.
test?
But this one only, Sensei. The summaries of viscoelastic matrix properties.
Mm, okay. They don't have any value of
To
GC.
design.
Temperature, static, response contribution, dynamic, strain reading. So information is not enough to understand.
Yes.
Okay. And
Yeah.
one moment.
Okay.
this a paper you found?
Yes.
Any other paper with the viscoelastic shear damper?
I will open all. Viscoelastic.
The same author.
Same author.
Uh-huh. But how about another author? Is there any other research?
ちょっと待ってください。
No.
Sensei, this one, it shows some damper properties for the viscoelastic.
Okay.
So they have like they use how can I say 3D model. So if you can see here, they have 3D model and they have two direction, north and east, west, and they have two different length and different stiffness and see coefficient of damping and the fuse for the supporting both side. The fuse mean in between the this is the fuse. So they have viscoelastic material and the fuse steel fuse.
Okay.
It's a little bit different from our model, but at least they have some properties. Yeah.
Okay.
Yeah.
The author is the same author.
The author is this one is McKay Christopoulos. McKay Christopoulos, and this one is this one. The same sensei
Same author.
Christopoulos. Yes.
Okay.
Mm.
I understand. Okay.
It
It's
also used Kevin Jot model.
something unique device. Can I share my screen? I want to.
Okay, sensei.
Right. Yeah. So, so. Yeah. Can you see my my handwriting?
Yes, sensei.
Can you see?
Yes, sensei.
Yes.
Okay.
So, so this is a coupling wall.
Mm-hmm.
The beam here, and so this is a coupling beam. But we want to put some damper here.
Yes.
Before it was a hysteresis damper.
Mm-hmm.
And now we want to introduce viscoelastic, right? Viscoelastic. But the device in the paper, it is a kind of a combination of one part is steel, hysteresis, and one part is
Visco.
viscoelastic.
Mm-hmm.
It's a kind of a composite. And why they do like this is this viscoelastic velocity and the force is like a straight line
Mm-hmm.
with one, I forgot, C, C, well, one coefficient. Okay,
Mm-hmm. Yes.
so it will go actually infinite.
Yes.
So, but they なんていうのかな usually in case of oil damper, we consider this kind of second slope
Mm-hmm. Yes.
so that the damping force doesn't go excessive. Okay, so we intentionally put this kind of upper limit for damping force,
Mm-hmm.
or we use this kind of nonlinear hysteresis. So in this case, F equal C multiply velocity alpha power.
Okay.
So in this formula, it will
Mhm.
go,
Non-linear.
yeah, non-linear and going to be flat.
Mm.
But it looks the device in the paper
Mm-hmm.
is just one coefficient
Mm.
and going up infinite. So to avoid excessive damping force,
Mm-hmm.
they combine steel damper.
Mm.
Yeah? So you know, if shear force F is so this F and this F is the same, right?
Yes.
Because it is connected in series, right? So if F is exceeding this upper limit, so damping force doesn't go up. You understand?
Yes,
So
sensei.
there's a limit of damping force
Mm.
because hysteresis damper has a limit.
Yes.
So this is a well good idea actually, good idea
Mm.
to combine. So they confuse. So fuse is electric device to break in case of excessive electricity, right?
Yes.
So it's the same mechanism. If damping force is go over this limitation, so this steel part will go non-linear, and the damping force doesn't increase anymore. Yeah, it's a very clever idea, but we have to adapt this one because there, way it's his idea.
Mm.
So I was thinking
Mm-hmm.
to instead of using this device, I was thinking to use this kind of viscoelastic damper here. And so instead of, as you know,
Mm-hmm.
それが何あるあ、どうだったかちょっとわかんないね。So if you select steel beam, and if you select the beam, you can get you can get viscous damper. You can see
Yes, sensei.
the damping force is C multiplied velocity power
Alpha.
of A.
Yes.
So if A is 1, it's a
Mhm.
straight line.
Okay.
But if A is less than 1, it will be some kind of a curvature.
Mm-hmm.
So but we want to know the value of this coefficient.
Mhm.
Well, えっと and the viscoelastic damper is very popular for, let's see, not the coupling beam. We usually use it for shear wall.
Mm.
For example, in this case,
Mhm.
this is a high-rise building,
Mhm.
and this blue part is
Mhm.
damper, and this is a kind of shear wall.
Mhm.
Upper part and the
Mhm.
lower part is sandwiched,
Uh-huh.
and there is a viscoelastic material between these plates,
Okay.
sandwich part, and it will resist against shear deformation or shear velocity. So, so this device is very common. So I think that there must be some. Well, we can use the same material for this.
Mm.
I don't know.
It looks the
Maybe.
same.
So, I found this one. This is a hysteresis damper for coupling beam. So, like this. It's also boundary beam is steel beam. So nonlinear damper for steel in the middle. I mean, in the between. It's very interesting, isn't it?
Mhm.
There
Yes.
are one, two, three, four, five shear wall,
Uh-huh.
and the bottom part is almost pin supported, very slender,
Yes.
right? So it's easy to turn over, but they're connected by damper.
Temper.
Actually, this
Mm.
building already constructed.
Oh.
Yeah, but this is so. Anyway, the damper is hysteresis damper. Yeah, hysteresis damper. Maybe. Yeah, but I want to. Okay, okay. So どうしようかな。
Can we use uh that the same data from the paper? The properties. The
Excuse
properties.
me?
Can we use the same properties as the viscoelastic in the paper?
Which paper?
I will show my screen. This one, Sensei. So this is the properties. Except
Yeah, but
yes.
uh, this device is combined with the steel damper. I mean, fused element.
Mm-hmm.
Without the fuse, I mean, damping force will be excessive. I mean, too much.
Okay.
So yeah, we can use this damper, but It looks weird. なんていうのかな。This device is his own
Yes, yes.
original device.
I mean, only for the viscoelastic without the fuse. Is there because there is not much properties catalog for the viscoelastic damper. Viscoelastic damper usually designed based on how much thickness the viscoelastic and the metal plate in between the viscoelastic. So if we can find those properties, maybe we can put in the Stera 3D.
Okay, let's ask opinion of, manufacturer. I
Okay.
have some friends,
Okay, Sensei.
manufacturer, and they produce viscoelastic damper.
Mm.
Zakira-san, did you go to Oiles company?
Yes, Sensei. We go together.
Yeah. So we can ask Oiles.
Okay, Sensei.
I believe they also produce viscoelastic damper.
They have viscoelastic wall. The visco wall.
Yeah.
Remember that.
So we can ask them
Yes.
how about using same material for coupling beam,
Okay.
and we want to do some numerical study, and if it's effective, maybe they can manufacture.
Okay. Okay, Sensei.
So, and if it's success, they will be happy also.
Yeah. I will also will have to find the properties for viscoelastic more detail. Okay.
Okay.
Thank you, Sensei.
So, okay. I will share my screen.
Okay.
So, so please think about the displacement based design for viscoelastic damper.
Okay.
Yeah. So the procedure is same.
Yes.
You push over
Yes.
until target group. Okay.
Yes.
And you can draw pushover curve and SA, SD. Yeah. And this is the target drift. Delta D. And in case of hysteresis damper, you check ductility factor of wall
Okay.
and ductility factor of coupling beam. You remember?
Yes, Sensei.
And you obtain damping
Yes.
from both ductility factors. But in case of viscous damper, there is no
Beam.
ductility factor of beam.
Okay.
Actually, this viscous damper, damping force is a function of velocity.
Okay.
So static analysis velocity is zero. Right?
Okay.
So actually no damping force. So how do you get the damping factor at this target drift? So this is a how to say question, and you must
Determine.
think about.
Okay, Sensei.
And Naki-san
Yes.
do something like this. Yeah? So from this target point, you can get omega.
Omega. Yes.
So this slope is omega.
Yes.
And if you know omega,
Mhm.
you can get the velocity.
Okay.
So velocity is, なんだwell, deformation multiply omega, just omega.
Okay.
Just omega is a kind of velocity. And if you know velocity, you can get the, えっと、damping coefficient. なんだっけ。そう Ah, yeah. I remember. I sent you. So
Design damper using capacity spectrum.
どうだっけ
Is it document that you sent me last time, Sensei?
Yeah. You have a document now? Can
Uh,
you open?
okay.
Maybe not
This one. Design damper using this one, Sensei. Design damper using.
Maybe. Could you go
Yeah.
down? Could you go
Yes.
down? Yes.
Mm.
Yes. And yeah, this is a definition of equivalent damping. And in case of, could you go down?
Mm-hmm.
Viscoelastic. Could you go down? Could you go down? Could you go down?
Okay. Here.
Could you go down?
More.
Could you go down? Yeah, this one.
Okay.
Okay. In case of this, could you magnify a little bit?
Okay.
Yeah.
Okay.
So actually, this is very complicated formula,
Mm-hmm.
and damping force is equation 18.
18.
I mean, under sinusoidal sine, movement. And one cycle energy is equation 19.
Mm-hmm.
So, but it's very complicated to calculate this integration.
Yes.
So, Professor Kasai proposed the simple formula, equation 20.
Mm-hmm.
Yeah, equation 20. And potential energy is equation 21.
Mm-hmm.
So finally, the damping coefficient, equation 22, is calculated from this formula. Okay.
Okay.
So we use this formula.
Okay.
Okay? If we know target deformation, so it corresponds to amplitude A, and if we know omega from the slope
Mm-hmm.
of capacity curve,
Mm-hmm.
and we can get the equivalent damping from this formula. えっと but we need some design. I mean, value of C,
Value
and
of
value
C.
of alpha.
Alpha and C.
Yeah. So, okay, I will say propose some viscoelastic material, and I will give you coefficient C
Okay.
and alpha.
Okay, sensei.
You use this material for coupling beam, but this property is just temporary.
Okay.
I will ask oil company exact value for material properties, but for the moment I will give you temporary values.
Okay.
So anyway, you can start calculation.
Okay, sensei.
Then. And one is the time history analysis by using Stella 3D, and another one is displacement-based design using equivalent damping coefficient, and we can compare the result.
Okay. Yeah, I also have run again check the calculation last time. So this one for the 10-story. So this is steel beam, and then we check from 0 until 75%, and the
Okay.
damper is adequate at 50% and 75%, and when go to 75%, the straight line is a little bit up. It's probably due to this action here. If you can see under L central, the 75% at the bottom story is already exceeds the drift limit, but for 50%, all the drift is less than the maximum drift for all the earthquake. So we can, in my conclusion, I can say if the blue line is less than the capacity curve, we can say that the building have adequate design performance. Or it also, if it's lower, it's probably over design.
Mm. So in this case, you calculate the damping coefficient.
Yes.
Equivalent damping.
Based on the formula that you give to me, Sensei. I will open this one. Which one? This 10-story. This one. For example, 75%. So for the concrete wall, we use Priestley formula. This one,
Yeah.
and this one based on formula that you give from bilinear.
Linear
Yes.
hysteresis.
Yes.
Okay.
Sensei. Yeah.
And you took average by
Yes.
energy.
Yes. Yeah.
And uh, there's another, I mean, no- except the energy, average by energy, there's another way to get the system damping by using coupling ratio.
Coupling ratio. Yes. They also have, but from Priestley, Sensei.
Yeah. So
I
after you get the damping
yes.
coefficient of wall
This one.
and beam, you
Compare with the this one, Sensei.
yeah.
This formula. Okay. I think I have to check the coupling. Let me see. So here, for example, this one.
I'm just curious.
What's the difference?
Yeah, what's the difference?
Okay. Okay. Here I have the moment overturning energy. Not this one. Sorry, the other one. So, so from here, energy. Okay, the moment overturning here. So for example, this is 45%. So if I can input here 45%. So this damping is about 10%. And yes, it's a little bit different since it's For the Priestley book is about 10%, but based on energy equation is about 19%, 20, almost 20.
20.
Mm.
Energy average is a little bit, well, very large damping.
Yes. Do you want me to open the formula, Sensei?
No, it's okay.
Okay.
桜さん, you
Yes, Sensei.
must submit paper to Japan,
Mm-mm.
なんだっけ, Japan Association of Aerospace Engineering
Yes.
Symposium.
Symposium.
And deadline of abstract is May
8 May.
8th May.
Yes, Sensei.
So, yeah, I wonder, you can write a paper even now using this stamper.
Okay.
And maybe also you can write paper by viscoelastic damper.
Mm-hmm.
But viscoelastic damper, maybe it takes time.
Mm-hmm. Yes.
So maybe next paper.
Okay.
So please think about writing paper, not abstract. Abstract anytime you can write, but
Yes.
in case of full paper,
Mm-hmm.
I don't know how many pages for the symposium. Do you know the page number?
It's about 9 pages. Last time you said it's about 9 pages.
Yeah, maybe.
Mm.
Yeah. So please start writing paper.
Okay, Sensei.
Okay.
So the additional for the paper is instead we use the hysteresis, we use the viscoelastic damper.
Yes.
Okay.
Yes.
Okay, Sensei.
Okay, Ataya-san, do you have anything?
Yes, Sensei, may I share the screen?
Yeah. Ataya-san, you also submit paper for symposium. So
Okay, Sensei, if it becomes 8 or 9 pages.
yeah.
Sensei, the paper you sent us, the contribution is TMD floor system that take advantages of both floor isolation system and TMD, but does not require additional TMD mass. This is the mathematical model, which is the same as the land mass model in Stera 3D. And this is the matrix of stiffness. And this is the BI vector, but this is the stiffness matrix of a system with multiple TMD and Elias and Matsuga 2014. But when I formed the stiffness from both those formulas or those forms for my 7 degree of freedom model, it is different, I think, because in this paper the location is also involved, but not in this stiffness matrix not. So I think it is more correct, the first one, because the stiffness of dampers are related to the floors that TMD is attached to. For example, third floor, sixth floor, and seventh floor. So this stiffness are related to the floors that those TMDs are attached to. In Elias and Massawa, it's not like that. It is like started from the top and become lower and lower. And I don't know what do you think, Sensei.
No, if you use Stera 3D, you don't need to worry about the stiffness automatically.
Yeah, but I just wanted to know the theory. Okay, anyway, and the optimum location of TMD. The left hand is the same as multi-mode strategy, that when in the OI mode, for example, first, second, and third, when the amplitude of the mode shape is the largest, that is the location of TMD. But these authors proposed another approach also. In this approach, they find the separation between two neighboring and resonance, which is located the right hand and left hand of one omega. And then when the separation between those anti-resonance frequencies are the largest, that location is also considered a candidate for the optimum location of TMD. And then if these two approaches are the same, this is okay. But if not, then again a resonance frequency of the model which the first TMD is attached to is calculated. And again, this formula is used. If it is smaller than the right side, then optimum location is the location that is achieved by the right side hand approach. But if it is not, then the LC1 and LC2 is the same, like this, and we finally find the optimum location for TMD. For example, these are the mode shape of first, second, and third mode. In the third mode, we can see that the uncontrolled in the second mode, here is the first, second, the third floor has the maximum amplitude, so this is the location. And the anti-resonance frequency separation are also calculated. We can see that the third floor has the maximum or the largest value of the separation of anti-resonance frequencies. So these two are the same, and the third floor is the location. But in here, in the first mode shape, we can see that the top floor has the largest magnitude, but the anti-resonance frequency separation is the largest in the sixth floor. So we don't know which one is better. So we use the first TMD to the top floor and calculate the frequency of first mode and second mode, and use from this formula and decide from these two if it is smaller or larger. But in this case, in this example, this is not smaller than the right side, so the optimum location is the same as the first approach, the sixth floor.
Sorry, Ataya-san, I couldn't follow. What is the separation?
Separation, since each frequency of each mode has two anti-resonance frequencies, one in the left and one in the right side. So the difference between those two anti-resonance frequencies or the separation.
For example, location 1 is 6.25, another one is 16.71. So that you can say difference is 10.46 from this table.
Yes, Sanjay.
And what is 6.25?
This is the anti-resonance frequency that is located in the
anti-resonance frequency. What does it mean, anti-resonance frequency?
this is the figure sensei that I found when the frequency response function of a system is calculated. This is the figure. This is, for example, the peak. If you consider, this is just for 2 degrees of freedom, but if there is 3 or 4, for example, this is the first frequency, first mode shift frequency. This is one anti-resonance frequency, and there is another anti-resonance frequency.
Anti-resonance frequency.
Yes, sensei. The anti-resonance frequency is where that when excitation is applied in that anti-resonance frequency, the response of the structure is 0.
Oh.
But it takes more study, I think. So each frequency of first mode shape and second mode shape has 2 resonant frequency on both sides. The difference of those 2 frequencies are the separation of resonant frequency, which is calculated in here. So when the separation of those 2 resonant frequencies is the largest, for example in here, the third floor has the largest separation of anti-resonant frequency, so it is considered the location of TMD.
So this is the idea of whose idea?
This paper's author's idea, I think. Or maybe they have some references. I don't remember, but this is an approach, I think. Maybe it is they say because anti-resonant frequency are the representative of neighboring frequencies. For example, if you consider the second mode frequency, so the first mode and third mode frequency has some effect on the third mode frequency. Because of that effect, we consider the anti-resonant frequency.
Tanaya-san, do you know anti-resonance frequency? Have you heard?
Yes, sir. I have means in the frequency response function curve between 2 resonance conditions.
Yeah.
There is one peak on the negative side where the response is very less. I think that is referred to as the anti-resonance frequency by some researchers, and I think that region is more suitable for the structure because the response is very less. I am not very sure about it.
So they propose decide the location of TMD using this anti-resonance frequency.
Yes, sensei. But in this model, the 6-story model,
Yeah.
these 2 approaches are the same finally. For example, in third and second mode, in here, LC1 and LC2 is the same, but in the first mode, in here, LC1 and LC2 is the same. Maybe this case that LC1 and LC2 is not the same must be very rare, but it's not clear. But I think as they brought some reasons, they said that anti-resonance frequency are the representative of neighboring modes. When neighboring modes are so sensitive to some excitation, then the response of the middle mode shape will be affected by those neighboring mode shapes. So it is better to involve the antiresonant frequencies to find the best location.
Okay.
Can I say something? So,
Yeah, Saraya-san, please.
sir, here what I find from whatever is presented here by the author, I think when the two anti-resonant frequencies are separated far apart, the region of resonance in between them will have a greater bandwidth.
Yeah.
So they are trying to place the TMD there such that resonance peak comes down,
Okay.
so that they have a greater effect on the frequency spectrum.
Okay.
I think this is what the author is
Yeah.
trying to do.
Yeah. Yeah, it's reasonable. Okay. Okay. So Ataya-san, you want to try this method or?
Yes, maybe sensitive. But there is something, for example, in the third mode, this three mode shapes are the uncontrolled mode shapes. But this line is the controlled mode shape of the third mode. We can see that uncontrolled mode shape, the second floor has the maximum amplitude than the fourth floor. But control mode shape shows that the fourth floor has the maximum magnitude. It changed, but as I showed in two previous meetings, it's a little bit difficult to find the mode shape of controlled structure because the displacement of TMD is also large.
Yeah, you asked me to get the controlled mode shape. Yeah.
Yes,
Yeah.
because in here second floor is selected because the uncontrolled mode shape shows that the second floor has the maximum amplitude, but the controlled mode shape shows that fourth floor has the maximum magnitude. So they installed the TMD to second and fourth floor and compared. So they realized that when we install the TMD on the floor that is selected by control, mode shape is better. And also TMD's optimized parameters, they found this frequency response function of the displacement relative to the ground by Fourier transform. They found the frequency response function of the interstory drift by this formula, and finally found a function which is the maximum of max of interstory drift of all floors. Based on this, for example, consider that the third floor has the maximum magnitude of interstory drift. So interstory drift is related to omega and also to damping, and they use the gradient list optimization maybe by MATLAB and find frequency ratio and damping ratio to control the interstory drift, because they say that the interstory drift is very related to the damage of the building. So it is better that the TMD parameters have to be optimized based on the interstory drift displacement. But they didn't present it more about the optimization method. And these are the performance indices, which is frequency function, responsive interstellar drift, and also frequency response function of the acceleration, absolute acceleration of damper, and absolute acceleration of the main structure. They studied two numerical cases. One, that all floors are designed as TMD floor. For cases, uncontrolled TMD floors attached, it means that all floors are considered TMD floor system, and same amount of damping maybe didn't presented so much detail, but it means that conventional TMD is installed in all floors, at all floors. And another case is 10%, the damping ratio of the structure is increased to 10% from 1%. And it showed that when all floors are considered or designed as TMD floor system, give the most effective or give better result. And this is also max acceleration. In this case also, when all floors are considered as TMD floor system, give the minimum amount of acceleration.
Okay.
And another case, they use multimodal approach to find, they wanted to use just three floors as TMD floor system, and found the specification for those three TMDs, which is third, fourth, and sixth floor. So in this case, also when three TMDs, three floors are considered as TMD floor system, give better result than when it is considered two or one. Compared to the uncontrolled building. And the acceleration also shows that the floors, for example, third, fourth, and sixth floors, when considered as TMD floor scheme, the acceleration are minimized compared to the non-controlled and or the cases that on that floor, those floors are fixed. And they also did an experiment model, which is not, the pictures are not so clear. This is a very small scale frame used from plexiglass material. There is a roof, and on the roof there is attached a floor, TMD floor. TMD floor is attached to the frame by some springs and also dashboard. And under this floor system is some linear ball slides. And they found the accelerations, recorded the acceleration. And in here that when the floor is fixed or floor is considered as TMD floor, this is the effectiveness. It is very high. It means when the floor is considered TMD, the acceleration is reduced considerably. But since I couldn't understand it is practical, because they said that with such optimally designed parameters, the TMD floor do not only serve as normal floors, but also might get the response of the main structure. And also said floor slabs are attached to those considered beams through stiffness and damping devices if they work as TMD floor slab. Consider this is a frame, a room, for example. This is the main primary beams, and these are the secondary beams. this is TNT floor attached to the secondary beams. They said that, for example, maybe it was under Cover Creek, the stroke length is 50 centimeter. If we consider 50 centimeter stroke length is needed for TMD floor, so we need about this area that this TMD floor should be vibrating. So how this floor can be serve as normal floor? Or
Maybe it's a kind of a local isolation floor.
since I don't understand because this TMD needs some space. When, for example, this frame is laying this side, this TMD floor have to lay in the left side, so it needs some space to sway. In this case, maybe I don't understand or it is not practical. I couldn't understand, Sensei.
Why you don't understand?
Because Sensei, when consider Sensei, this is, for example, your office,
Yeah.
and this is the slab. So this is slab when the frame, for example, vibrates.
Yeah.
This slab have to vibrate counteract.
Yeah.
So it needs some space, for example, Sensei, and this four direction, two direction, and
Yeah.
four.
So they put to 50 centimeter space, right?
Yeah, for example, if otherwise this floor system will hit to the wall, and it is not possible.
So this floor is not connected to the wall.
No, it is. They said, for example, connected to the secondary beams, these beams. But for example, these secondary beams are fixed to primary beams, and primary beams are connected, fixed to columns. And this
Actually, there is a floor, of course, under this TMD floor is a kind of another additional floor.
So if it is additional floor, it is not. They say that we don't add additional mass. We just use from those normal floors as TMDs. It means that we don't use another floor. If we use, for example, the second floor, then it is not practical because we add some other mass.
Yeah. Well, butなんていうのかな。Yeah, you are right. You are right. You are right.
Yes, it's. But when, for example, the building has a large, for example, mass, then maybe this TMD floor needs more straight length, more than 50 centimeter.
You think so?
And for example, if this is the door of your office, Sensei, how you can reach to this TMD floor? This have to be a hole, for example, Sensei. Then I think it's not practical, but if I don't understand, I don't know. But as I imagine, it's
Okay. Yeah.
or maybe if Saranya-san has some ideas, I don't know.
So actually, I am also thinking about the same thing that it is very difficult to arrange such kind of system. Also, another thing I couldn't understand is there would be many columns, right? In a building. So is this floor only a part of the whole floor system surrounded by 4 columns. Or I don't think any column can go through in between these floors.
Yeah, this secondary beams are also additional mass.
Okay. Yeah.
Yes, sensei, but I thought if I didn't understand if it is practical, then it is better to find some frequency ratio and damping ratio optimal that some researcher has studied. And these are studied in the range of mass ratio between 1% up to 15%. So when we can use additional mass, for example, 40, 30, or 50% of mass, then we can derive another expression for frequency mass ratio and damping ratio. And also, there is in some papers there is said that usually we use a mass ratio between 1% and 10% because less than 1% is not effective and more than 10% it is not practical because large mass is not practical. So if this idea works, then why we cannot find optimized expression for a mass ratio as well? Then if we, for example, use optimized mass ratio, optimized damping ratio, optimized frequency ratio, then maybe we will get a better result. But the main thing is that this idea might not be practical. But in multiple TMD sensors, this is, for example, Toyota 101 that they have seen before. If we imagine, for example, as an example, this is the floor, there is just a small space is considered for TMD, but in this, other floors can be used for other purposes, offices, for example. And for example, in the model that I worked, a 7-story, there was one on the top, one on the sixth, and one on the third floor. So if we consider the TMD location in here, for example, if we use from this kind of TMD, then it will be very small. For example, if we use from multiplication of participation factor and effective mass ratio, the first TMD, which is on the top floor, has a little more, a little large mass. So if we consider a cubic form of TMD mass, is 2 meter, is 1 meter, and height is 50 centimeter, very small. For TMD2, for example, which is very small, 80 centimeter, 50 centimeter, and 37 centimeter is also small. And TMD3 is, for example, 50 centimeter, 30 centimeter, and 18 centimeter. It occupy a very small place. And we consider it in the middle of the building, which is the center of gravity. There's no problem for an installation of multiple TMDs.
Okay.
And that's all, Sensei.
Could you show me the slide again? It's very interesting. The slide of previous one. Yeah, this one. How did you? Is it a? I mean, where did you find this picture?
This picture is in a paper that is. This is the link. There is said kind of TMDs. Many type of TMDs, for example.
Okay.
Because Sensei, you asked me in the previous meeting that how it is practical that install multiple TMDs in many floors. So, for example, we consider at this kind of space for elevator, we can consider the same space for some TMDs. And it's also not in all floors like elevator. In some spaces, it doesn't occupy a lot of spaces.
Okay. Yeah, yeah.
Yes, I'm not finished.
Very good. Very good. Okay. By the way, I still try to derive the formula. You remember?
Yes, indeed.
Very complicated. But なんていうのかな。いや、
Sensei, did you see the file that I sent?
Yeah.
I think the method is okay because the calculation in Excel shows the same results.
Yeah.
But solving that equation with many row and if you write it in one line, it becomes from Toyohashi to Nagoya, and it's very long.
Yeah, but I don't satisfy without knowing, I mean, the answer. So, okay. Anyway, so, so what kind of additional work you want to do?
Up to now it was dependent on the being practical of this idea. If it was practical, I wanted to work on finding some expressions for optimized mass ratio.
And you analyze the second story only?
Yes.
How about increasing number of story?
I was also thinking about, for example, a 20 story.
Yeah. Because you are discussing about the higher mode effect. So I think second story, actually first mode is dominant. So I think you should consider much higher building.
Yes, I think 20 story is good.
Yeah, 20 is good. 20 is good.
And also, since I'm thinking about the how to distribute the stiffness of stories, it is linear, okay?
Yeah, I sent you the document how to.
Yes, Sensei.
But the first mode, yeah, you must assume triangular shape.
That approach is okay, Sensei? For 20 story?
So, let's see. I have another document. I mean, not the triangular. There is a paper which use another shape of mode shape. And I will send you.
Okay, thank you.
I will send you the information. Yeah. So please analyze 20 story. Okay.
Okay,
Sensei. And maybe
Sensei.
you can write a paper 7 story and 20 story.
Okay, Sensei.
Okay. So Saraya-san.
Yes.
So after you come to Japan, well, anyway,
Yes.
you have any plan?
Yes,
I
sir.
mean, any place you want to visit in Japan?
Oh, no, sir, not right now.
But you stay only, I don't know, uh, less than half a year, right?
Yes, sir.
So
Yes, sir.
hmm, let's discuss where to visit because
Yes.
they are the largest shaking table in Japan in the world. Maybe
Yes.
many students want to visit there, so I can arrange some study trip. Also, if you visit the Tohoku area, you can see tsunami disaster, you know, place and how
Yes.
it was recovered now. Yeah, it's very impressive.
Yes, that will be great.
Okay, and also you must consider research work. You will,
Yes, sir. Yes.
yeah,
Um, Sir, may I share my screen?
yeah, yeah, yeah.
I wanted to add something to what Atesan was discussing
Mm.
regarding the practicality of the dual mass dampers. So, so this is the paper which I was working on right now on the hybrid control using base isolation and tune mass dampers. So in that paper, I will directly go to the figures. So I had actually considered a real life hospital building in New Delhi in India, which I have already shown, I think, in one of the presentations, where I was using the unbonded isolators to isolate this building. This is the plan of that structure. Then I use the unbonded fiber reinforced isolators to for the base isolation of that building. And then when I wanted to add the TMD, I wanted to make it practical. So just not like a single model of the TMD. So I, similar to what Adesan has done, I have actually calculated the mass and the dimensions of the TMD considering steel material, and I have placed the TMD inside the building. So this would be a ground floor of the structure where I have found out the dimensions of the TMD based on the story height that is available and also counteracting the stroke length. Now, what happens is that kind of stroke length was not possible using a single TMD mass because there are columns in between. So I divided that TMD mass into 6 masses, and now I could accommodate a single TMD system using same stiffness and damping and same mass elements, and I could get the controlled results from that using this kind of practical system. Actually.
Is this TMD is only one direction?
Yes, yes. So this study was only conducted in one direction. However, for two direction also similar stiffness and damping elements could be arranged in the opposite direction and guide rails could be provided for the bi-directional response.
Okay.
So
How
this
do you are you thinking to analyze this building? I mean, by frame analysis?
Yes, so this I actually this is already communicated and is under revision. So this work has already been done. Hereby, I have not conducted a optimization study. I have conducted the optimum tuning of the TMD directly to the fundamental frequency of the base isolated structure. So this was one of the preliminary studies which I did. This was a
Oh, connection is something wrong. Please. Maybe Ataya-san, you can also try frame model and put the TMD inside the frame, not the lamp Thomas model.
Yes, Sensei, I just said once, and you said it's better to start with landmass and
Of course,
item.
of course, of course. I don't know how to put the DMD in Stellar 3D. Yeah.
If it is possible, it maybe give us more ideas because in the frame it shows more practical.
Oh, Saraya-san connection is lost. Well, as I found this paper. Can you see? Sorry, it's in Japanese, but this is a typical high-rise building. Weight distribution, almost the same weight along the height, but the stiffness is a little bit going down along the height, and the shear force, I mean, is going down along the height, and well, they simply put some, how to say, assumption. Well, it's a linear change. Then they consider 40-story and 60-story high-rise building by using this assumption. So they don't use any model shape, but this is very simple actually. And
Since there is any formula for finding stiffness of each story,
uh, えっと、えっと、let me see. Well, first you assume some value for k, and you can calculate natural period t, and you can adjust k, increasing and checking natural period, and to satisfy, this is the target natural period empirical formula. So you adjust k to find out, I mean, natural period is equal to this target value.
since h is the height of the building,
H is the height of the building. Yeah, yeah.
okay, since could you send this file? Maybe I will translate it. It's just 3 pages.
Of course, this is not. I mean, I don't know. It is one proposal, but it was proposed by a structural engineer in Japan. So he knows many buildings. So maybe from his experience, he proposed this distribution. Okay, I will send you. So please check. Okay.
Okay, sensei, and also there was another paper that Edison-san showed me. There was another formula for nonlinear distribution of stiffness. Maybe I will check that also.
Okay. 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 Saraya-san, sorry, your connection was.
Yes, sorry, my connection got disrupted. So can I share my screen again?
Yeah.
Yes. Sir, as my research plan in Japan was to first devise the hybrid system with base isolation and TMD, then to obtain the optimized and robust hybrid controllers for lifeline structures under earthquakes and winds, and then to propose the design guidelines for performance-based structural design using the hybrid control systems. So what I have made one preliminary plan, since you can comment on this. So first I wanted to write one basic paper on the optimum tuning of the TMD under multi-hazard scenario of earthquakes and winds, and this could be a conference paper to the 18th World Conference on Earthquake Engineering in Milan, in Italy, 2024. So, sir, here what I am planning is since my uh, isolation device is trilinear in nature, so there is one doubt on on which frequency should we tune our TMD. Should it be on the first frequency or should it be on the second frequency? So I was actually conducting some preliminary investigations, and what I found is that the second frequency is always good for reducing the base displacement under here means severe earthquake excitation. However, for slight to moderate wind conditions, the structure does not vibrate so much to go into the second frequency. There, the first frequency is more important. And in the first frequency, I don't have significant amount of damping. If the structure vibrates like this, you have also pointed out this in one of the meetings.
Yeah. Oh, connection lost again.
I'm really sorry, sir. I don't know what is happening. Yes, so in the first frequency, if we tune our TMDs to the first frequency, then I am getting considerable amount of reductions under wind excitation also. So I wanted to investigate that for a conference paper, and after that, as we were planning, we could propose some machine learning based optimization procedure for the optimum design of the hybrid control system. You were suggesting some of the papers of the Bayesian based methods, so I could review them and I could find some optimization method for this hybrid control system. And finally, I want to do some probabilistic analysis where I could find the fragility curves for the different uncontrolled and only base isolated and hybrid control system. So this part I am planning. I could finish the first conference paper, I think, within 1 month, because I have conducted a lot of these simulations already. I could just refine those results and I could write in part of a conference paper. And then the rest of the things I think I could complete in 5 months. I will try to do that.
Okay. Are you intend to use Stera 3D or you use MATLAB?
Sir, sir, for the optimization, I think we can use MATLAB or Python, and then for some case study, we can use that TMD in Stera 3D and find out the response. I think that could be done.
Okay. Okay, good. Good. So we can discuss in detail after you come to Japan.
Yes, yes.
Okay. Any other discussion today?
Yes.
Right now, I sent you the document of high-rise building model. So please check. And so today is 18. So next week, Saraya-san will come. Okay. So maybe we will have a meeting. I don't know, 27 or 28.
Yes, sir.
So, which one? 20, how about 28 afternoon, 1 o'clock?
I'm okay,
Or
Sensei.
Yes, sir.
27,
I think 28
28?
is okay. Yeah.
Okay, 1 o'clock is okay?
Okay, Sensei.
じゃあ、コントロールグループ、1 o'clock. Okay.
Sensei,
Yeah.
do you have any for Sarah-san? Yeah. I already teach her about the capacities and spectrum. Yeah.
But Sarah-san will must write bachelor thesis
Mhm.
and maybe about the coupling word.
Okay.
Yeah. So mm, maybe it's better to ask her to read Priestley's book.
Yeah, I also asked her to read Priestley's book about
Mm,
the design spectrum with coupling beam.
mm,
Sorry, the displacement design with the coupling beam.
yeah.
Yeah.
And every time at the control group meeting,
Yes.
I want to ask Sarah-san to make a short report
Mm-hmm.
about what she studied.
Yeah.
Yeah. So next meeting is the 28th. So Sarah-san, you please prepare some short report. I mean PowerPoint slide. Okay. So Zabura-san, please help her.
Okay, sensei.
Okay. Okay. So see you next week.
See
Okay.
you,
Bye bye.
sensei. Thank you.
Yeah.